All right, so let me show you this one here, which is classic machine learning. Not the large language model, but the older kind of machine learning, which is more specialized. And that's ML100. And in this one, we're going to use Google Colab. So actually, I'm going to switch to a different browser that's logged into a different Google account that I prefer to use for this stuff. All right, so here's so we're going to, this is something I was very glad to learn about. Google Colab is free online Python environments hosted by Google. And this is great for students. It doesn't matter what machine they have. It doesn't matter what version of anything they have. They can use this environment to write Python scripts. So you make a new notebook. These are called Jupyter notebooks, and they have various features. I only know how to do a few simple things on them. Now you get an environment. You can just write Python code and run it here on the Google servers. And so the first thing to do is import this library called TensorFlow. TensorFlow is the machine learning library that does this work. So I import TensorFlow. Let me make the font bigger. All right. And I just print the version just to show that it's working. And you see it's initializing. It's given me some RAM and some disk. It gives you what looks like 12 gigs of RAM and a disk of 107 gigs, all for free. And there, it's done. It has imported the library and printed out a version number 212.0, which just shows that it's able to import the library. And now we can do some machine learning. And this, I was amazed, is just what scientists do. I used to be a research scientist long ago, and at the fundamental, this is what a research scientist does. You measure something, like the temperature of some gas or the pressure of some gas as a function of temperature, and you just get a series of measurements, and then you fit some kind of curve through it. So here's some numbers. X goes up and Y goes up. And so you see if X is minus 1, Y is minus 3. And if X is 0, Y is minus 1. And if X is 1, Y is 1. So when a human looks at these pattern of numbers, you notice that when X goes up by 1, from say 1, 2, 3, Y goes up like 1, 3, 5. So it looks like when X goes up by 1, Y goes up by 2. And when X is 0, Y is minus 1. So a human can sort of figure out that Y equals 2X minus 1. And that is the process we want the machine to do, that kind of learning, where it looks at a pattern, looks at some data, finds some kind of pattern, and figures this out. But it's going to figure that out without anybody programming this equation anywhere in the code. That's the point here. And it turns out all you have to do is about 10 lines of Python to do that job, which is amazing. But like everything in Python, it's easy because somebody else has already written a library that does all the hard work. So if you put in this code, and I can just put it in on top of this code, that's one way to do it. All right, so it's going to import TensorFlow and NumPy and a couple more things. Here it's going to make the model. And this model, it's a neural net. It's simulating neurons in a brain, but it's going to have one neuron that just takes data from X and predicts Y. And it's going to use this thing called standardized general gradient descent. I have the first word wrong. This is gradient descent, and loss is mean squared error. Here's the input data. Just what I said, here's the X values, and here's the Y values. Then it's going to fit it in 500 cycles, and then it's going to predict a value for X equals 10. So if you run this, here it is going through 500 cycles of optimization. Now, if you go back to the start, I'm trying to scroll up. Here we go. All right. If I go back to the start, what happens is it guesses something about the model. It guesses how Y might be related to X, and then it measures the loss. The loss here is just the mean squared error. How badly did it miss predicting? And so it's trying to lower this loss. And as you can see, it's pretty effective. After it does one calculation, it then changes its parameters to make the loss smaller. And as you see, it went down by quite a bit. And as it goes, it gets this loss down to a really small value after 500 cycles of improvement. It's going to reach a very small loss, like 10 to the minus 5. And at the end, it's going to predict a value for x equals 20, I think. Let me go back to my code. It got 18.97. I'm just going to remember that. If I get to the top, which I'm having trouble getting to the top. All right. There we are. That's what it predicted for 10. So since the model, the right answer is 2x minus 1, the right answer for an x of 10 is 19 for y. And it got 18.97. So it's very effective. Now, of course, this is just a simple linear relationship with no noise, no errors, so it shouldn't be too hard to figure it out. But this is how it works. X comes in, it has a slope and an intercept, y equals mx plus c. All it's doing is determining these two parameters, the slope and the intercept of a linear relationship. So the perfect answer is a slope of 2 and an intercept of minus 1. And you can print out the results and see what the network learned. So if you do it again and print out what you learned at the end, then when I get down to the bottom, here's what it learned. The correct answer is 2 and minus 1. And as you can see, it got within 1% of the right answer of 2 and within 1% of the right answer of minus 1. So it's not perfect, but the point is it figured that out without a human having to figure it out and program it first, which is what we've been doing in computing for all this time. So now there's just some challenges. You can add learning with errors. So now it will not be able to roll it a loss down to 0. And you'll see it still gets pretty good, 1.99 and close to 1. But because there's some random variation, it gets some errors. And then you can try fitting a parabola. Now here is the ys. So if I just change the ys to this and get a parabola, let me just do that. Okay, so I'm not going to use this. I'm going to use this instead and try fitting that. And now, all right, this is a curve, and I'm trying to fit a straight line through a curve, so it's not going to fit very well. And you see the loss doesn't get very small. Before, the loss got down to like 10 to the minus 5. Now the loss doesn't seem to get any smaller than like 4. It's not very successful at fitting it. And if we go down a little more, we can now fit a curve and draw the curve. So here's a more complicated curve and a more complicated machine learning model to fit it. So get rid of this old code and put in new code. All right, and now we've added a little bit more to it. It's got some plotting libraries. So here it's going to create noise. It's going to take x times cosine x, which is going to be a wavy curve that gets bigger. And then it's going to add some randomness to it, 0.1 times some randomness to it. It's going to make 1,000 points on this noisy curve, and then it's going to try and fit it with a much more complicated neural model. And I think I have a picture of it here. Well, there'll be a picture coming up. Let me bring up a later project that has a better picture. I think it's here. Yeah, this is what I wanted to show you. Now instead of having one neuron for input to output, you have layers of neurons. You have the input go to some neurons, and then intermediate neurons, and more neurons here. So these take data from some input, these take data from various other inputs and combine them. These take data. This is very much what your brain does. It has layers of neurons, each of which takes signals from the previous one, and you have all kinds of parameters. You have a weight for every one of these intersections. So you get a lot of parameters. And in this case, we have one input neuron to take x, then we have 64 neurons in the next layer, and then 64 neurons in a third layer, and then one output layer. So it's got what's called 128 hidden neurons inside that do calculations to connect the input to the output. So now it can, in principle, model very complicated relationships between the input and the output. And again, it's going to just figure out, based on the input data, what values it should give all those parameters. And here it tells you, the model at the top, it tells you what's going on here. You have two parameters here, a slope and an intercept, 128 parameters in that hidden layer. Let me get back to this thing, keep scrolling off the screen. All right, 128 parameters there, 4,160 parameters here, so the total number of parameters is 4,355. This is commonly used to rate the size of a computer learning model. The more parameters it has, and the more parameters, the better in general. So now the loss gets pretty small, see it shrinking, and here's the result. Just what a human might have done. The data is all the blue dots, and the model is the red curve. So it was pretty successful at figuring out the pattern here. And if you go ahead, there are you can try it with different number of units for layers and see what happens. And you can vary the amount of input data and noise and see what happens. And that, I think, is very interesting. And this is the classic machine learning, where your machine learns to do something that it would have taken a human to do otherwise. I'm going to stop this video.